All right, so we're looking to prove the triangle sum theorem. And that's the fact that the three angles in a triangle, this A that's right here, plus B, plus C, all of this stuff totals up to 180 degrees, right? A fact that we've known for quite some time, maybe learned it in another math class, like 6th grade, 7th grade, something like that. But what we haven't known is why it actually is true. So it's based on a very unexpected thing, and that is the parallel postulate. And the reason why is this. Let me explain. So we've got only these three angles, A, B, and C, and we're trying to prove that they add up to 180 degrees. But we don't have anything to work with. There's absolutely nothing else in this picture to help us. Well, one thing that we know adds up to 180 degrees or measures 180 degrees would be a straight angle or a straight line. And that's what I want to do is I want to add an extra line to this picture. And the line that I'm going to add is going to go through point C, and it's going to be parallel to this base that's down here. And I've got a postulate that tells me that I can draw one of these things in here. One and only one. And that's the key to this proof, is that we have to add in a line that goes through point C. Look at that, it's perfect. It goes through point C and is parallel to this base. And the parallel postulate allows me to do that. It says that there's exactly one line through point C that's parallel to AB. And that is, at least in Euclidean geometry, that's true. Okay, now as a matter of convenience, let's go ahead and number off these other two angles here. And then we should be able to see here that these three angles here total up to 180 degrees, right? And this is very similar to if you did that little investigation, if you did that little investigation where you tore your triangle apart, this angle A basically went right there, and this angle B went right up there, right? Back that up a little bit. Right, and that's exactly the technique that we're going to use in order to prove this thing. So we need 180 degrees from this, and we're going to get that from the linear pair postulate. Now, the linear pair postulate, the middle word there is pair, which means that we can only use two angles at a time. So the way that we're going to do this is that we're just going to pair up two of these things. Like we can pair up one together with C here to make one complete angle, and then we can add that thing into angle 2. In order to do that, let's add in a couple of letters in here on this line. How about F and G here? So that I would have the measure of angle FCB should be equal to 1 and C added together. Right? 1 and C. Yep, that looks about right. And that is the angle addition postulate. Right, so there's one thing that we're going to use. And then the other thing is the fact that we've got parallel lines. The whole reason why I put that in there is that when we cut parallel lines with a transversal, we get ourselves some congruent angles. And so specifically, angle 1 that we created up here is going to be congruent to angle A here. And angle 2 is going to be congruent to angle B here, because those things are alternate interior angles, right? Alternate interior angles are congruent when we have ourselves parallel lines. All right, so I think that we've got enough of an outline of this in order to actually write our 2-column proof for this thing. So let's get started here. So we want some statements. Right, and reasons. All right, this has thrown me off a little bit that I didn't center this, but you know what? That's okay. So I'll just move it up. that looks about right. All right, so we're starting off with the fact that we have triangle A and B, C. That's given to us. Okay, and if I look back at my plan up here, I needed to draw in line FG through point C parallel to AB. I've got to actually write all of that stuff down. So draw auxiliary line, I called it FG, through C that is parallel to AB. What allows me to do that is our parallel postulate right up here. And I'm going to put that as the reason. Okay, and so now that I have that line in there, now I can use the fact that angle A and angle 1 are going to be congruent to each other, and angle 2 and angle B are going to be congruent to each other. So that's what I'm going to write here on 3. Angle 1 is congruent to angle A, angle 2 and C, 2 and B. And that's based on the alternate interior angle theorem. That if you have a pair of parallel lines cut by transversal, then pairs of alternate interior angles are congruent. All right, so we're having to make ourselves an equation here. I have congruent angles. I need to use the definition of congruent angles to turn them into their measurements so I can do some substitution and whatnot. So measure angle 1 is equal to the measure of angle A, and the measure of angle 2 is equal to the measure of angle B by the definition of congruent angles. How many times have we used that thing? All right. So now let's start making our equation here based on the linear pair postulate. And on the linear pair postulate, we wanted to use 2 angles. One of those things is going to be this FCB, and the other one is going to be angle 2 over there on the far right-hand side. So measure angle FCB? Yes. CB plus the measure of angle 2 is equal to 180 degrees, and that is because of the linear pair postulate. Okay, but that's not exactly what I wanted here. I wanted 1, C, and 2 to add up to 180 degrees. So here's where that angle addition postulate is going to come in handy. On number 6, that the measure of angle FCB is equal to the measure of angle 1 plus the measure of angle C. Number 6. That's the angle addition postulate. Now we can do some substitution. I can take out this FCB and I can replace it with the measure of angle 1 plus the measure of angle C here. That's what I'm going to do on step 7. So measure angle 1 plus measure angle C plus measure angle 2 is equal to 180 degrees. All right, and that was substitution property. Okay, we're so close. Now, let's go back up here and look at the order. I kind of want to mimic this order here that's A, B, and C, except for C's kind of in the wrong place. And I can actually switch these things out because it's addition. And addition, the order of it doesn't matter. That's called the commutative property. So if in your proof you didn't put that in there, you know, it wouldn't make such a big deal about it. But I'm going to be as thorough as possible. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle C is equal to 180 degrees. Again, I just switched those two out. What allows me to do that is the commutative property of addition. Okay, now we're almost there. I think this last step should do it. I'm going to take 1 out and right here, replace it with A. I'm going to take 2 out and replace it with B. So I've got the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees, finally by substitution property again. All right, and there we have it. There's the proof of the triangle sum theorem. Key idea is that it was based on the parallel postulate. Parallel postulate, again, only works in Euclidean geometry, which will have consequences for elliptic geometry and hyperbolic geometry. So since this whole entire proof is based on this concept of parallel lines, that means that in these other kinds of geometries, as you will see, their angles and their triangles are not going to add up to 180 degrees.